So you're all PhD students?
Postdoc.
Postdoc? Yes. In the area of computer vision or more or less?
Yes.
This could be more general interest, computer vision, maybe also sensors. Sometimes there's laser scanners, it's also electromagnetic rays, and also call this vision or something like that. Okay. Now we'll wait for our host. Is integrated in the digital room?
Yes.
Just to read the message, I think. The paper, instead of staying there. Okay. So sometimes I will use the clipboard, but I will take only that piece, because this is out of the field of view. So maybe this is a better place. I will make large drawings.
Okay, did you start already?
No. I was just explaining that when I use the blackboard, that will be this part.
Okay.
So maybe the position is not.
I think we are going to start. Usually we wait up to 15 minutes. Professor, I'm just going to introduce Professor Rudi Penne. So I'll use his own description of himself. So Professor Rudi Penne has been trained in mathematician at the University of Antwerp, which is of course in Belgium, where he received his doctorate in 1992. In the twilight zone between algebra, combinatorial and projective geometry, and mechanical applications. His current position is as a logical continuation of distinctive research. Professor of the Faculty of Applied Engineering for the University of Antwerp. His main field of interest: computer vision, geometric modeling and calibration, projective line geometry, projective especially line geometry, rigidity theory, and combinatorial computational geometry. A significant portion of his time is also dedicated to popularization and communication of maths to a broad public. Thank you.
Thank you for the introduction. So let's start. And I chose to put the main contents, my main message, rather in the beginning. First of all, these are the main characters of the story. So, search of revolutions, but not pointwise, but linewise. So they're just constructed by rotating a sweeping line. And as a matter of fact, this is the most general situation. And I think the best way to show this is by rotating this line around the fixed axis. And then you see you have this hyperbolic intersection. Maybe we can pause it.
Don't drop it.
And also this line. Here you see that there's straight lines. Okay. Now, and this is a special case where the center circle is pitched to a point. This is just a circular cone, and then this top is like at infinity with this cylinder. Okay. Now, because we are talking about rotations, and rotations around an axis, and these rotations are described by angles. The core of the story is just situated on a circle. So we take 3 points here on a circle. Now, as a matter of fact, it will turn out that only the relative angles are important, but for the moment, let's have notations for the sides of the triangle. And now I'm going to make affine combinations. And of course, you know the plane. If you have these affine combinations, you can come up with any other point in the plane. You have, for instance, here point P1, P2, where each of these points are affine combinations, which are, as a matter of fact, 3 multiples of the 3 points, which are normalized such that they sum up equal to 1. And if you choose all the coordinates positive, so 3 times positive, then you have a point inside the triangle, and we call it a convex combination. But if you play around with also negative numbers, just be sure that the sum equals 1, then you also have points outside. But now, suppose you don't want to generate the whole plane, but only the points on the circle, then we call these coefficients affine. So these are the affine coefficients. And we call them affine circle coefficients if D belongs to the circle determined by these 3 non-collinear points. So that was something I was looking for, generating other points by using only the angles and only using linear combination of the 3 points. And I was looking for a stable parameterization. And okay, so this is what I found. The proof is not so difficult, but that you have 2-degree polynomials in some parameter t. So you can. This means that you have only 2 degrees of freedom in the coefficients, normally for the plane. But if you restrict the result of the circle, you have only 1 degree of freedom. And just to make this clear, I will write it down for the first coefficient. Then I have just in the denominator, I have always the same. I have here minus b squared plus a squared plus d, and then I've got minus a squared d squared, and in the first column I've got here this a squared d minus a squared d squared. Okay, so this was just to compute x here. So this is, once you have those 3 points, you have these rational functions with numerator and denominator of degree 2 in a parameter, and this is a way, this is what I called circle affine or affine circle coefficients. Indeed, one can also easily see that the addition of x, y, and z results to 1. Okay. And it's also easy to see that you can express all these entries of the matrices directly to the relative angles. So if you have a bigger circle with another origin or whatever, as long as A, B, C are distributed on the circle with these relative angles, then you always have the same coefficients. So for a new point t. So it are just these relative angles of t with respect to A, B, and C, which determine those three coefficients. So this will be a way how we will deal with rotations. We have three angles. This will correspond to measured data, and we will compute a new position, a new rotated position by these circle coefficients. Now, I did this on MATLAB for an easy. Did it yesterday just for an example. Here I have ABC. Just with 90 degrees intervals, and then you can find if you use these coefficients, x, y, and z in the previous slide, if you choose t between 0 and 1, you've got this blue arc, and then the green arc between b and a. All those points d are generated by t between 1 and 2, and so on. And then if you have t larger than 2 or a negative t, then we have this yellow arc. So you can generate every point on the circle. Okay, if t has a nice geometric interpretation, for instance, if you have your point d here, you just intersect d with a, you join d with a, and you intersect it with the line bc. And this point of intersection, lying on BC, gives also affine coordinates, but then on the line BC. And this affine coordinate t is exactly the parameter t which was here, which here appears in this theorem. So this t. Here this t is exactly the same as this t. Yes? Is the singularity on minus infinity and plus infinity? On the circle? Yes. As a matter of fact, for plus infinity and minus infinity, you have here this south arrow. Yes. That's true. Now, okay. So you could say it's just one more rational parameterization of the circle, but it is expressed as linear combinations of three of its points. That's what we need.
Just a question. What is the impact of this singularity? Just like to combining measuring angles on a circle?
No, it's like the point here where you have the tangent parallel to AC. So no, excuse me. Here you have AD parallel to BC. So this is the singularity where m comes to infinity. So this is the point joined with A, which is parallel to BC. So now if A, B, and C are positioned otherwise on the circle, you also have this other singularity, but this will be always the intersection of the line through A parallel to BC. Okay, as a matter of fact, this is my main message already. So if you, sorry, I do this. So if you have now a root surface of revolution, so if for selection, a choice of 3 angles, it corresponds, it's associated with 3 lines, then you can use these same affine circle coefficients, but now applied not to the points, but to the lines. And if you make this linear combination of the lines, instead of generating the points on the circle, if you apply the coefficients to points, now you apply the coefficients to lines, and you generate all the other lines. Yes? And I think the remaining of the talk is more or less an explanation of this. And this is true, whatever, it's also true for the cone, it's also true for the cylinder. Okay, this is the spoiler alert. And why should we care? Because a lot of sensors, they have this rotational symmetry. For instance, here a LiDAR where you have even a lot of lasers rotating. So you have several cones or hyperboloids. Hyperboloids, I don't know, I should have checked this before. But also here, this is of particular interest for us. When you have a fixed laser, which is controlled by rotating 2 mirrors. You have a fixed laser, but if you rotate the mirror, the reflections, they have rotations. And if the if the rotation of the rotating line is not exactly intersecting the rotation axis, you don't have a cone, you have a hyperboloid, but we don't care as long as you have 3 of the lines of one surface of revolution, you can generate the other lines. And this will be a way to model and also to calibrate these kind of laser scanners, because its line model is composed of surfaces of revolution, root surfaces of revolution. And instead of taking care, so this is from an article where they had to calibrate, let's say, the physical parameters, and instead of taking care to determine the intrinsic parameters and all the kind of distances and at which angle the fixed laser enters the first mirror and so on. All those things you don't have to take care of it. You just observe triple of lines instead of triple of points, and your angles is something you can control in these rotations. And once you have these angles, you also have these circle coefficients. And once you have these circle coefficients, you know the other lines without having to get into the details of the calibration model, of the physical model. You don't need, so the physical model is a black box. You use the geometric structure of the lines, of the data lines. This is the story. So here, for instance, 2-mirror Galvano laser scanner, where Galvano driven. This means that this is the way how the rotating mirrors are activated, and then you have one fixed laser. And as a matter of fact, these are kind of coaxial hyperboloids, and this axis is the axis of the second rotating mirror. And then you have for each incoming laser, because you have a fixed laser that it's already reflected by the first mirror, for each incoming laser, you have another surface of revolution generated by the second mirror. So you have a family of these, you have a 2 degrees of freedom family of surfaces of revolution. after each of them, you can use triple lines to generate it. Okay. Now, we are talking about a very Euclidean story because I'm not talking about any quadratic or whatever, just surfaces of revolution. So maybe it's a little bit strange that my tools are from projective geometry here because it's a Euclidean story. But maybe it's also because I have a kind of tunnel vision when I like to use this projective geometry, and I can connect this projective geometry to the Euclidean geometry interpretations by using, first of all, a choice of the plane of infinity, and secondly, which is mostly in practical situations, where you have a 3D world situation, and you extend it to projective space, you have a notion of your plane of infinity. So you can more or less return from your projective geometry to your real Euclidean space. But I will also use weights. This will be it will be weighted projective geometry. And this will be also the key to use my circle calculus, because this circle is typical Euclidean object. So you know that projective geometry is for perspective drawings, and you also know that these are the French mathematicians who formalized the tools by the Renaissance artists. And we know, for instance, the projective plane is most clear that, as a matter of fact, a projective point is nothing but a view direction, viewing to a Euclidean point, and if this view plane or projection screen is just removed, all you get are only the rays of view direction. So this is called a projective point, and you will use these double points. I think it's more or less common for homogeneous coordinates. There are a lot of advantages for this, but two advantages already for us are that we have something more than Euclidean geometry, you know, the vanishing points. But as a matter of fact, in projective geometry, you don't have the distinction between points of infinity or finite points, but this choice is already added coming from our real world. Because if you drop the standard projection plane, then you don't know what direction is a vanishing point. But if you agree to have this standard position, then we know that the vanishing points are view directions which are missing this Euclidean plane, which are parallel to the Euclidean plane. So these are the view directions ending with 0. So this is something the choice I will make for the homogeneous coordinates, also in 3D. The last 0 will correspond to point of infinity. This is not forced by projective geometry. This is an additional choice that we made to be able to return to the Euclidean geometry. And another thing is that we can have weights. So that first, I will talk about the weights in a minute. So we can, instead of just looking to a point, a projective point is also a point in a sense, but if we also have this choice of a particular vector of homogeneous coordinates, we can also assign a weight. This weight is the scalar k, and this can be interesting. For instance, in computer vision, this weight corresponds to the depth of the point on the image plane, that you can attribute the depth to this image point. Also in kinematics, it's interesting if you have infinitesimal rotations about the center, this weight can be associated to an angular velocity. So there are a lot of ways to interpret the weight, and so we have Euclidean geometry, but what we add are vanishing points and these weights. This is for us important important motivation also for me to go to the projective geometry. So in 3 space, we have 4 homogeneous coordinates. We have the convention that the last coordinate 0 will correspond to the vanishing points in our real workspace. And we also have projective plane coordinates. These are these homogeneous linear equations. But instead of equations, we like to use coordinates. And of course, this is a 4 vector, it is also a 4 vector, but these are 2 4 vectors living in another space. But it's one of the charms, one of the advantages of projective geometry, that there is a confusion between the point and the plane notation. So this is just nice. And projective geometry uses this confusion as an additional tool, such that it's called duality. You know, if you have a theory about points and planes, you can reverse the words, you can interchange the words points and plane, and you have another theorem that will lead to the same proof, almost also with the same notation. So this is the plane at infinity. So this means that here we have a normal vector, ABC, but we don't have a normal vector for the plane at infinity. And then also for lines, we will use Blücher coordinates. As a matter of fact, we have a direction and a point to determine the Euclidean line in 3 space, but it's very common to eliminate this arbitrary choice of this point of representation. And we do this by taking the cross product of this point with the direction vector, such that you have a moment, and whatever point you choose on the line L, you come up with the same moment. So this is a way to eliminate this maybe a little bit annoying free choice for P. So then we have a moment and a direction vector. And of course, you can rescale this direction vector, but this scalar multiple will also be taken into account to compute the moment. So as a matter of fact, you come up with 6 homogeneous coordinates. Also believe this is, I don't want to give more details, I believe this is more or less known, that a line in 3 space can be represented as by a point in projective 5 space. So these are 6 coordinates, 6 homogeneous coordinates. So as a matter of fact, this is a 5-dimensional space, but in a projective setting with homogeneous coordinates. Most often, if you don't like this homogeneous representation because it's determined up to a scalar, normally normalize this. This can be done with a Euclidean line. And then you have this direction vector. You can normalize this 6-tuple by a scalar such that the direction vector is a unit vector. But then you still have the 2 senses of this direction. You still have 2 orientations for the line. So you could say that this normalized Blücher vector is a representation of an oriented line in 3 space. Okay. Also interesting is, which was not a problem for points and planes. Sorry for this again. As long as you take care that your 4 vector does not consist of 4 zeros, each 4 vector can be interpreted as a point or a plane, no problem. But for a line, you have this additional condition, the Graf-van-Blücher relation. The scalar product of the first 3 and last 3 coordinates must equal to 0. It is a quadratic relation. This means that the lines are considered as points in a P5, in a projective 5 space, but lying on, this is a quadratic relation, lying on a quadric in P5. So sometimes you see people drawing something like this, but this should be imagined in 5 space. This is called a Klein quadric. These are all the points in P5 which satisfy this quadric relation. And the points here on this quadric, they correspond to lines in 3 space. Okay? But of course, you also have other points lying not on this quadric, and they also have an interpretation, but I will talk about that. Now, this is more than we will need. But it is, as a matter of fact, an overview of the weights. If you want to have your projective geometry, let's say a Euclidean false, this can be done, so you can more or less do some Euclidean geometry within the setting of projective geometry. If you first of all have this distinction between finite points and point at infinity, or finite planes and planes at infinity, the plane at infinity, this is something which is not natural present in projective geometry. So if you make this additional choice, just by choosing one plane in projective 3 space, you say, from now on, this is the plane at infinity. And if you also attribute some weights, so if you have some points here, then you receive the difference notation. Here I use these semicolons, these just to make clear that the coordinates are determined up to a common multiple, so that only the ratios of the coordinates are relevant. And if I really choose a particular weight here, then I have vectorized my geometry. So I go from geometry to algebra, kind of vectorization. The homogeneous coordinates are here represented by commas. So this is, let's say, in a real far space. This is just a real far vector. But there are, you see that there are separate conventions for the weights. If you have a finite point, then the weight can never be zero. So then the weight is the value of the fourth coordinate in the selected vector. But if you have zero here already, then the weight is equal to the norm of the vector which is made of the 3 first coordinates, the first 3 coordinates. So I just normalize here by this norm, this vector, and then I make sure that I have the correct weight. Okay? And for planes, it's vice versa. Then the normal weight is done by the norm of this first vector, ABC, but for the plane at infinity, the weight is given by the cross coordinates. And also for lines, just the most important is for finite lines, we can normalize here the Blücher vector, and then if we use the scalar W, then W is what we call the weight of that line. If I'm talking about projective geometry and I've just got some line, first of all, I don't know whether it's finite or line at infinity, and let alone that I know something about the weight, because if I multiply everything by 10, I still have the same line. So it's the same geometric object, but when I vectorize it, then I can define what I mean by the weight. Okay. Now, these are the operations I will perform. The problem is that most of these operations, maybe none of these operations, is well defined in projective space. So there are no geometric operations, but for have a well-defined mathematical operation, I must first vectorize the points or the planes or the lines by choosing a weight, and then I can do the operations. And the result of the operation will have a geometric interpretation, but formally, the result of these operations will always depend on the choice of the weights. So for instance, if I've got a point and another point, I can do the addition, but this is just the vector representation of the points. And then I have a point always a point on the joining line, but I can, as a matter of fact, this is not geometrically determined. If I choose other weights, I have another point, but I always have a point on that line. As a matter of fact, by playing around with the weights of the first point and the second point, I can generate every point on that joining line. For 3 points, I also always have a point on the joining plane. If I mean there is a condition, if those points are collinear, then they do not determine a plane. Here, if those points coincide, they do not determine a line, and so on. Here, addition of 2 planes, then I've got a plane through the common line. I will never do the addition of a point with a line, or a plane with a line, or a point with a plane. You have a theory how to do this, and then you're not talking about lines and planes, but you're talking about pieces. But as a matter of fact, from an algebraic point of view, these vectorizations of the points and the planes and the lines, these are antisymmetric tensors which belong to different algebraic exterior products, so they are not added to each other. Okay, maybe this is also nice if you have 2 lines, and if they intersect, then the resulting line will be going through this point of intersection. As a matter of fact, this line will also lie, this is not here, it will also lie in the same plane, going through these 2 initial lines. If you have 3 lines, you have a common point, then the addition will. The exact line always is the same story. The exact line is not defined geometrically by these geometric lines, but if you choose some weight and you have a vectorization of each of the lines, then the choice of these weights will determine what exactly line you have here in the result. But it's always true that the resulting line will go into the common point, if there is a common point. Those 3 lines they form a bundle. You have 2 kinds of bundles. There's a star. If you have 3 lines going in the same plane, then if you add those 3 lines going to this line in the same plane, the result will always be a line in the common plane. And this is very interesting here. If the lines do not intersect, so they are also not coplanar, so we say that 3 lines are pairwise skew, then they determine a root quadric. They generate a root quadric. That's why this is even true when it's not, this is projective geometry, it has nothing to do with surfaces of revolution or so. Just any root quadric, maybe a saddle surface or whatever, and any projective root quadric is swept by a line which is the result of the addition of 3 skewed lines. So, and if you here use coefficients for the weights of these lines, you can generate whatever line you have. So this is already an interesting thing we will need. That's why I was looking for affine combinations for the 3 points on the circle. Because I could translate this to affine combinations of those 3 lines, generating a new line on the quadric. But most cases, the result of those summation is not a line. So those three lines are lying like this on the Klein quadratic. And if I do the addition of those three lines, consider as points in P5, I can also, most likely, that I come up with a point which is not on the quadratic. But if this is a line, if the result is a line, then this is the line on the quadratic generated by these three lines. Okay. These are the sums. The result always depends on the attributed weights. I have products, which is also nice. For instance, if I've got 2 points, I can find the line coordinates by taking particular vector of homogeneous coordinates. So this means that I choose a weight, also define the weight, and then this exterior product means that the result, I start with 2 points, but the result will be a line, it will be another object, another nature. So I can find the 6 line coordinates of the resulting line, which joins point A and B. So this is the geometric situation by taking these determinants. Okay. The nice thing is that this resulting vector will of course depend on the charge of the 2 points on the line, and it also depends on the weights I've chosen for A and B in these vectors. But nevertheless, other choices will always generate the same 6 vector up to a common multiple. So considered as homogeneous coordinates, it's well defined. So this is an operation how I compute from 2 given homogeneous coordinates of 2 points in free space the homogeneous Brücke coordinates of the joining line. I can also do this with a point and a line. I won't give the details here, but I've got a point, 4 coordinates chosen weight, also have some line, and then the result of the line and the point can be computed. I can just always also using the trick, the key for making this happen is by, this is also done here, is by labeling the coordinates not as 1, 2, 3, 4, 5, 6, but using double indices. And for the plane, the coordinates are also not labeled 1, 2, 3, 4, but the coordinates here are labeled by triple indices. So this is a kind of trick to make this operation on homogeneous coordinates really work. And so you can immediately find the homogeneous plane coordinates starting from a point in a line. So you can also have the exterior product of 3 points, and then you come up with a joining plane. Sometimes you also, this is also kind of exterior product, but it's a dual product. This is the join product, but you can also have the meet product, where you meet, where a plane meets a line, and these are formulas using the plane coordinates and the line coordinates, and you immediately have a formula which is very similar to this of joining a point in a line, because these are dual operations, and you find the point of intersection. Now, this is an interesting way. So suppose you have here 2 points, A and B, and suppose it are finite points, and we use here normalized coordinates. This means that the vector representing these points, has weight 1. We also do this for this one. Yes. Then we can have these exterior products of the 2 points, computing the line coordinates. We come up with a direction vector in a moment, determining the line. Okay. Then this direction vector exactly equals the vector AB, or B means minus A, which means that the weight of this line, which is defined as the norm of the direction vector, is just the distance of those 2 points. If you moreover choose a weight here or a weight here, then the weight of the connecting lines also, these weights also propagate to the weight of the connecting lines. So you have here, let's say, a projected way to compute the homogeneous line coordinates of 2 points. But you can have Euclidean, by also taking the weights into account, you see that the resulting vector, the vector of the line, has a weight which has a Euclidean interpretation because it's the distance between the 2 points. Another example is this. Suppose I've got here a plane alpha with here a normal vector. And suppose I've got here some intersecting line L. Then, if I now compute the intersection of the point, I compute the point of intersection of the plane with the line. So this is the ridge. It's also an exterior product, but it's the meat, we call. Then the weight of P can be proved or observed, it's easy. It's just the dot product of the direction of L and the normal vector. So once again, purely from projected geometry, the intersection point here of a line and a plane, but taking the weights into account during the computation, you also have these. You also have this geometric information about the angle of the intersecting line and the normal vector of the plane. Okay. Now I'll have to make. Yes, sometimes they crash if I, for instance, I've got a point and a line. You can have the join of a point and a line and you have a plane, but if the point is on the line, then this joint will be a zero vector. Sometimes you crash because homogeneous coordinates are not supposed to be all zero. But sometimes this is the result of your computation. This means that the plane does not exist, determined by the point and the line. So determined is wrong terminology in this case. So this just means that the point and the line were in a kind of similar position. This is also the case if you have the intersection of a plane and a line. If the line is lying in the plane, then also the meat here will be a zero vector. Okay, and then finally, we also have these scalar products. The exterior products, then you have planes and lines and points. You do the exterior product, and your result is also a plane or a point. But the scalar products, they give just a scalar as a result. As a matter of fact, it's a pseudoscalar, but I won't go into details. For instance, you can have a join of 4 points, and you have a scalar, and it has some Euclidean interpretation about the volume of the parallel parallel. Yeah, it's not a parallelogram, but a 3D. I should call it a tetrahedron, but then it's times, it's a factor of the tetrahedron. Okay, but I don't want to talk about this. But this is also nice. This is just a scalar product of a point and a plane, and it's exactly 0 when the point is on the plane. And this is a nice scalar product of 2 6 vectors. And if this 6 vector actually is the Plucker vector of a line, then the graph Plucker relation is exactly equivalent to saying that the E product, the scalar product of the line with itself equals to 0. And if I've got two lines, then the scalar product is 0, even only if the 2 lines are coplanar. So this is also nice. So you can easily prove that by this, that if you have the addition of 2 intersecting lines, that the result is also once again an intersecting line. Okay, now I will make, pun not intended, I make the circle round by returning to the affine circle combinations. Okay, in the beginning, we have 3 points. Back to, so I was in projective 3 space, and now I'm back in Euclidean 2 space, in the plane. Sorry for this. I've got 3 points determining a circle. Then every other point of D can be generated by these affine combinations, where you have these rational functions, 2-degree functions in T, in parameter T, and T is, as a matter of fact, the parameter which describes this point of intersection M relative on this line BC. So, if we are given M, then we can find this D, so there's a geometric way to go from T to D, but you can also have this, you can also just do this affine combination and come up with the coordinates of D. Even if this circle is lying in 3 space, then A, B, C, and D, they all have 3 Euclidean coordinates or 4 homogeneous coordinates. Even then, you could apply these affine combinations just on the coordinates of these points. And you always come up with a point D on this circle. Now, suppose I've got here, this is 2 ways to make it cone. This is, let's say, an arbitrary cone. I've got a point T, a top T, which is not lying on the plane through that circle. Then I can make the join of T with whatever point on the circle. So this is making a cone, yes. But due to the fact that this exterior product, this was an important algebraic fact, I should have mentioned this. These are bilinear products. So this joint product or this exterior product of this sum can be distributed over the 3 terms like this. And this means that you have here the same affine combination that generating here point D using the 3 parts A, B, C. Now it's generating one ruler, one line, connecting the top with the point of the circle. And this is generated by an affine combination by the very same coefficients, but using these 3 rulers on the cone. But watch out, warning, these joints, these are vectors with a certain weight, and the weight is given here for to join 2 lines, given by the distance between the top and the point on the circle you're joining. And here you also have different weights. So if you just have those 3 rulers, you cannot use immediately the affine coefficients. You have to know the exact weight. So here you have to plug in not just any Plucker coordinates of these lines, no, but the Plucker coordinates of the lines with the appropriate weights. But therefore, if you use then a cone of revolution, so the top here is then, so you have this right cone, then all these weights are the same. So all these weights are the same, and you can, of this line, this line, this line, this line, you can even cancel the weights, so then you have these. So the affine circle coefficients, they work in any case, but then you have to use the correct Plucker coordinates with the correct weights. But if you have the circle of revolution, because all the weights then are equal, you can just use the normalized Plucker coordinates in the weight circle. This is now an easy proof for a cone of revolution, but it also can be proven for cylinders and for hyperboloids and so on. Our surface of revolution, you just can apply the same affine circle coefficients. And then, as a matter of fact, I can once again, now I have this affine combination on the rulers of the cone, and now I can intersect with the plane again. So I've got here this affine combination, but now for the lines, and now I intersect with the plane again. But this is once again an exterior product, which is bilinear. So then I have reconstructed the same combinations with the same coefficients, once again points. So I can return to the circle once again, but now I can choose to have another plane with ellipses, a parabola, a hyperbola. Okay? So this means that the weights you now have are different. You know, the weights are given now by, that's logical. What you have, the ellipse or the hyperbola, it strongly depends on the angle of the intersecting plane. So this angle of the intersecting plane, the angle relates also with the rulers of the cone. All these angles, these are the cosine of the angles, they determine the weights in this combination. So these affine circle combinations is from Euclidean geometry, but using the weights on your points, on your triple points, you can generate also general conics. And this is one more step. Suppose now you view. So these are, let's say, these 2-mirror laser scanner. You have this rotational symmetry. You have these hyperbolics or codes, family of codes, and so on, where the rotation gives the affine circle combination. Then the lines itself, they also satisfy the same affine combination. Then you do intersection with the plane. So these laser dots, once again, they have these the same affine circle coefficients. But then when you view it by pinhole camera, then first of all, you join all the points in the plane with your camera center. But if you have a relation of the points on the plane, in the real space, on your image, first you have these pinhole rays, so this is the joint, this is the linear. Then you have, these are the big L, these are not the laser lines, these are the viewing lines in the pinhole model, you have the same coefficients, and then you intersect with your image plane, so that this means that finally, the same coefficients of rotating laser scanner are just visible in the image of your pinhole image. And so you have this relation for the related image points. So it's time for my outro. I think I also started a little bit late. I think I stayed within 1 hour. If you have lasers generated by TV sensors, or it can also be rays of light captured by the 3D sensor. For instance, just a typical optical camera. Even if you have no pinhole model, maybe you can say that the points which are equidistant to the image center, they all form a kind of cone of revolution in your viewing. Then you have families of root surfaces, and this is my message again. It was also the beginning of the talk. All those affine circle combinations, the line triplets, they provide an alternative calibration model because I never needed, even at the end of the camera image or for the laser scanner, I never need to find intrinsic calibration parameters. That's the technical problem we are struggling with. You only have to measure the lines, you have to measure 3 lines, and you have to know the control angles, parameters, and then you have this formula of the affine circle coefficients. It's all about affine circle combinations of triple of points, triple of lines, and so on. Okay, thank you. Sorry for using my whole hour. I hope I thought I could start earlier. So nevertheless, thank you. Maybe. So maybe there's a question, I don't know.
Apart from the application of calibration, does this mathematical concept has any other applications to better infer it?
Another application? Yeah. For instance, you have this. Now I go back to the 2-minute laser scanner. You also have the target problem. This means that, for instance, this is used for vibrometrology, where you have to direct a laser to a certain point on an object, on a surface, and then you apply, you give some force to the object, and then the laser is pointing somewhere, and by means of the Doppler effect, you can measure material characteristics. So during 2 minutes. So what do you, so it's not only a calibration where you know if I have this pair of angles of the mirrors, then this is the resulting ray. No, you have you could call the reverse engineering, the target problem. You have a point in 3D, and you must immediately find the line on your surfaces of revolution. These are a family of surfaces of revolution. Which line will hit that point? So you will need to find the pair of angles. And this was, till now, there was no analytic solution for that. Because you have to use the geometry of the 2 mirror axes and the incoming laser, and it was with cosine and sine, and the reverse problem could not be solved analytically, so there were numerical procedures for this. But using just these affine combinations, I could find just a polynomial of degree 4 in the parameter t, and this is associated with 4 possibilities. There are 4 possibilities of angle pairs that generate a laser hitting, in general, hitting the same target. And so this is an example. Another example of application is this one. I mean, if you have, for, let's say, if you have a fitting, ellipse fitting, you know in an image you have an ellipse, and you want to do ellipse fitting, you have Fitchkable and so on. There are certain well-known algorithms for this. This would be a nice other algorithm where you have, you just have to find, it's a kind of minimal solver for a Ramsack algorithm for 3 given points. You must find the weights. You can generate the other points of the ellipse. And this is an ideal situation with a minimal solver of 3 points generating the other points of the ellipse. And I think this is a very nice application for ellipse fitting. And even, but then you have to find the weights also. Okay? And if you have found the weights of the points, you can also reconstruct. Just here, if you have found if you found the weights of this ellipse, you can reconstruct the top and the position and the distance of the top with respect to this circle. When it was, because it's an ellipse in your image, namely for instance, if you're viewing a ball, you have a circular cone, but in your image, this ball will be an ellipse, it occurs as an ellipse, and you can reconstruct then your optical center, and your principal point in your focal length can be reconstructed just by finding these weights and these affine circle coefficients. So there are a lot, too many applications for publication, as a matter of fact. Yes.
If I can add one more, can you go to the next slide, please? One more, please. Yeah. So, Professor Penne's explanation predicts all those colorful lines, but if what you are measuring in the lab deviates from those lines, then something is wrong. You don't know what, but you at least know that something is wrong. So, for instance, your mirrors are not perfectly plain, or the axis of rotation of mirrors, there's something loose in all, stuff like that, right? So deviation from the ideal situation would be a measure of quality of the device. So we could use this in production, just measure the few lines. If they fit nicely, okay, the device is good. If they don't, it's not.
Yes, because this, I've got here an if in mathematics, you can always start with if or suppose. But as a matter of fact, this never happens that you have these families of perfect ruled surfaces of revolution. Perfect cones, and it never happens. So that's why sometimes these impairments, these defects, even sometimes you can use these affine circle combinations as faulty control to see where something is wrong. But if your ideal situation is too divergent, too distant from the real situation, then you must use other techniques, and you cannot use this perfect model. Okay, but more or less, if you do a rotation, a laser or a rail flight, it are straight lines more or less. But of course, there are no mathematical lines, and these rotations. Okay. During the rotation of your device, maybe it will wobble, and maybe the rotation axis is not kept perfectly still. But I hope more or less these are more flexible assumptions than what else. But if you do those other calibration procedures to find, for instance, the intrinsic calibration matrix, then yes, then you of course assume something like a focal length and other assumptions that there is a mathematical focal length, that there is your lens has no width at all, everything is perfect. I mean, I think you're more, if you want to use a physical model, if you want to match your calibration model, then it's motivated by the physics of a device, then I believe that it's more dangerous to have yes, instabilities and so on. Okay. I also didn't know whether there were students here. I'm sorry for homogeneous coordinates and all those kind of things. I went through it, but I know that all these things were known. I didn't know about Euclid coordinates, but this is common to you. That's why okay. Yes, thank you. Thank you. Eerst die micro-apps.